All right, so this is chapter 18 of Matter and Interactions, where we're going to talk about electric fields and circuits. In this chapter, we're going to go through exactly how circuits and currents work, which will lead us into deriving those classic equations that are used so often to look at the current, the resistance, and the voltage. And of course, we have to start out with an excellent joke from XKCD about Benjamin Franklin's mistake about the direction that currents go. And throughout this, I've tried to find jokes. Some of them relate to the content, some of them are just ones that tickle my funny bone. So in this chapter, we're going to focus on calculating the electric fields of the elements in a steady state circuit. We're going to think about how we can depict these fields using vector diagrams. We're going to explain and understand the roles of charges on the surface of circuits. You're going to learn how to draw distributions of charges, look at the fields of steady state circuits, and we're going to apply the principles of the conservation of energy and the conservation of charge to analyze circuits quantitatively using their microscopic quantities. So we will be still understanding circuits from a fundamental physics perspective. So the first thing to know is that a circuit is not an equilibrium. So I've talked about this a few different times, but we're really going to see why that must be the case in order for us to turn on a light bulb. So if you apply an electric field to a conductor, any conductor, the charges are going to start to move. And this movement is determined by the direction of the electric force. Naturally, electrons will move with the field, electrons will move against the field, which we know from our electric force equation from chapter 13. And we have studied moving charges in chapter 14 that dissipated very quickly. So when you charged up your tape, it didn't stay charged for very long. However, we see that in circuits, the flow of charges is continuous. So one thing to think about is, what does it mean when charges flow, and what does it mean when something is charged? So charges in a circuit never reach equilibrium. The metal tries to polarize, but you want to keep it from polarizing. And essentially that means the net electric field can never reach zero. And so we're going to try to understand this aspect of circuitry from a microscopic level. So here you can see the electrons flowing around the circuit. And of course, this would be the opposite direction as conventional current. So we're going to dissect this by looking at current in different parts of a circuit. Don't worry, this is just another XKCD joke. We would never analyze a circuit that complicated with magic, smoke, and a 666 timer. All right, so I need to introduce something called the steady state circuit. So in a circuit, this current will flow at the same rate for a very long time. So you've noticed that when you've been building your circuits in your labs, that the brightness of the bulb will stay the same, really until either the battery runs down or the filament burns. So you get several hours of continuous current. Your circuits that you've been building are in a steady state. And a steady state is different than equilibrium. So equilibrium would mean that no current is flowing and that the drift speed is equal to zero, whereas the steady state means that charges are moving, but their drift velocities at any location aren't changing with time. So anyways, there's no deposits of excess charge. So by excess charge, we're talking about a charged wire. This is a little bit different than something than charges just moving. All right, so You can measure, and you have measured, the amount of current in different parts of a circuit using a compass. Since we know that the magnetic field of a circuit is related to the amount of current, you can measure the magnetic field, work backwards, and get the conventional current. So let's, for the sake of understanding these circuits better, consider a circuit consisting of two batteries and a bulb. An electron current flows from the negative terminal of the battery toward the bulb. So here in this diagram here, I like this particular picture because it shows both the electron flow as well as the direction of conventional current. So how would you expect the amount of electron current at location A to compare to location B? So you would have the batteries pushing around the electrons. They're going to go through this bulb, which has a resistance, and they're going to come out the other end. So there's potential answers for question 1. There could be no current in B. All the electron current coming from the negative end is used up in the bulb. The current at B is less than at A. Some of the current has been used up in the form of light and heat, or the current is the same at A and B. So let's break each one of these solutions down individually and see how we can arrive at the correct answer using what we have learned so far over the sequence of Physics 1 and what we've covered so far in Physics 2. So first of all, we need to think about what current is. Current is just the flow of electrons. That's all it's describing. It's just they're hitching a joyride going around a conductor. And so if that's the case, then can electrons be used up? Well, I mean, that doesn't make any sense because electrons can't be destroyed. That would be a violation of charge conservation. I mean, it's true you can have electron-positron annihilation, but that has nothing to do with circuits. That's something else. So that kind of discards a few of the solutions. What about, could electrons just accumulate in the bulb? So the current at B would be less than A. Well, if the current's accumulated in the bulb, then you would start to get a negative charge, and that would repel incoming electrons and stop the current. So the bulb is lit up, and using a proof by contradiction, we see electrons don't get used up. They don't stop at the bulb, so thus the current must be the same at A and B. And this type of reasoning that we just did is really vital to understanding this chapter, because sometimes the solution is obvious, but it's important to take the time and think, why is this so obvious? But you might be saying, what is being used up in the light bulb? I mean, we see light, so you can't get something for nothing. We have certainly learned this in physics. So it's time for everybody's favorite experiment. Rub your hands together. What change do you observe in your hands? Are they a little bit hotter? Is anything used up? And of course, the answer is energy. In the case of your hands and in light bulbs, energy is being used, or more correctly transformed, from stored energy into thermal energy. So in your hands, the chemical energy from your body is used to make heat, and in the bulb, the electrons are forced through the filament using battery chemical energy, and so they're shaking around all those atom lattices, and they're getting all hot and bothered and giving you heat. So there you go. All right, so now that we know that the electrons aren't getting up, we have what we need to start understanding current. So we can expand this now into circuits that have nodes, so little junctions where the current splits off. So we have something called the current node rule. In the steady state, the electron current entering a node in a circuit is equal to the electron current leaving that node. This is also called Kirchhoff node rule or Kirchhoff junction rule, and is essentially motivated by the fundamental principle of charge conservation. So, and I'll read it again. Kirchhoff junctions rule states that at any junction or node in an electric circuit, the sum of currents flowing into that junction is equal to the sum of the currents flowing out of that junction. So here's a question. I'm going to be posting the solutions to these questions online worked out. I do want you to try and attempt them on your own first. But suppose the steady state electron current I is equal to 9.8 times 10 to the 19 electrons per second. And at I4, the steady state is equal to 17.4 times 10 to the 19 electrons per second. What is I3? So we know that current must exist everywhere within a wire, but is it the same everywhere? And the answer is no. And let's figure out why this is the case. So we're going to look at this figure here, and we're going to assume that the directions of current are correct. If you ever get a negative answer for a current conservation problem, it simply means that you've assumed the wrong direction. It's actually flowing the opposite direction. And so you have current coming in at I1, and we see that it's splitting. So you can't have exactly the same amount of current in I3 and I2. They must both be less than I1, and then I1 would be equal to I4. And by the way, this works for conventional current as well. So we know that there's a steady state, but it does not mean that the current is exactly the same everywhere within your circuit. So this question, the answer will also be online, but this is a portion of a steady state current or circuit. What is the node equation for the circuit? Using that node equation, what is the conventional current at I2? And if I4 were 1 amp instead of 6 amps, what would I2 be then? All right, so let's do another example. In the circuit, the narrow resistor is made of the same material as the thick connecting wires. In the steady state, which graph correctly shows the magnitude of the electric field of locations around the circuit? So now we're understanding current flow with a little bit more focus on how resistors impact circuitry. And then likewise, in the steady state, which graph shows drift speed of electrons at locations around the circuit? So if you can think of a resistor as being a very skinny wire. So if you have a lot of water and then you're going to force it through a thin pipe, you would expect to then have a much larger electric field, which would then correspond to a much larger drift velocity. So a lot of what we're learning in terms of current flow does also hold for understanding fluid mechanics, which we'll see. I've got a short lecture prepared for later on fluid mechanics. So the electron current in thick and thin wires is the same because of conservation of charge, and therefore a smaller area will have a proportionally larger electric field. And since the drift speed is related to the electric field, then the electric field increases in this segment. And as I've already said, same concept holds for understanding fluid dynamics as well. Okay, so now that we have started to probe conceptually a little bit of the relationship of electric field and current, and we have a couple equations that we already know, let's understand this in more detail. So the electric field and current, we know that the average drift speed is equal to mu e, which relates drift speed to the electron mobility and the electric field. So electron mobility is, of course, material specific, and E is a field that you are applying. And so according to the momentum principle, once an object is in motion, no force is required to keep it moving at constant speed. So why do we need an electric field to keep a current flowing? So we've set the electrons in motion. but they don't stay there. And you already know the answer. If mobile electrons never interacted with the lattice of positively charged atomic cores, then once a current starts, it could flow forever. Actually, we are going to look at a case where this does happen. It's very cool, but that comes later. But what really happens is that the field starts the electrons moving and they just start bopping around into all of these little positive cores, increasing the thermal motions of the atoms, generating heat, just making a whole mess of things. So if there's no field to keep them moving, the electrons are going to stop. They're going to lose that momentum that they gained from having that electric force of the applied electric field. Well, then you might ask, I thought electrons made little negative fields. Couldn't these little negative fields be repelling all the other electrons? Could this make current flow? And you know the answer to this one as well. It's nice to be reminded about how much you know. And this brings me to question number 4. For 1 millimeter copper wire, the drift speed is equal to 0.935 times 10 to the minus 3 meters per second. And the electron mobility is equal to 4.5 times 10 to the minus 3 meters per second over newtons per coulomb. What is the electric field inside of the wire? So, starting to bring things together. A steady state series circuit has the same current everywhere. So when I say series circuit, I'm talking about a circuit that doesn't have any nodes. So electron current I depends on the cross-sectional area of the wire, which we've already seen before, where I is equal to NAV average. So then what does it mean for electrons to go from a thin wire into a thick wire? Again, this is something we've kind of already dipped our toes into, but if current must be the same in thin and thick wires, thus I thin is equal to N A thin V bar thin, which is equal to N A thick V bar thick is equal to I thick. So the average drift speed in the thin wire must be equal to the ratio of the area of the thick wire over the area of the thin wire times V average thick. So electron drift is bigger in thin wires than in thick wires. This is also true for liquids, but this is the opposite of how traffic works on roads. So anytime you have a large highway that has been narrowed down, everything grinds to a halt. That's not how water works. That's not how electric current works. So building on thick and thin wires, so if the electron drift speed is greater in the thin wire, how must the electric field in the thin wire compare to the field in the thick wire? Well, if drift speed is bigger, then the field must be bigger. So the electric field in a wire is following the wire. There's this relationship between electric fields and currents and circuits. All right, question 5. Suppose a thick wire is connected to a thin wire of the same material but half the cross-sectional area. If the drift speed of wire 1 is 7.2 times 10 to the minus 5 meters per second, what is the drift speed in the thinner wire? And if the electric field in the thick wire is 1.6 times 10 to the minus 2 newtons per coulomb, what is E2?
All right, so building on what we have, the field and current in the wire of the same material are uniform. So if we have these paths here, so if we go from A to B to C to D, and we calculate or from D to A then, and we calculate the round trip potential, we would see that delta V is equal to 0, thus implying that the field is also uniform throughout the entire section of wire. So we're going to build on that as we go forward. So they must be equal to each other. And this is true for steady state currents. Now this is different when we get to actually we don't do alternating currents, but alternating currents is what runs through the walls in this classroom and the walls of your house. All right, so going on to section 18.4, we're going to look at what charges are making those electric fields inside the wire. We know they're non-zero, otherwise we would not have current. So here we can see both the directions. You can see traditional current in this picture, what direction it would be going, and then what direction positives and negative charges. So as I've said, I've tried to fill this slideshow up with as many pictures to cover concepts both in this chapter and then just general concepts for physics too. All right, so we need to start thinking about the steady state circuit. So we know that there must be a non-zero electric field in the wires, otherwise charges wouldn't move. And then we know the magnitude of E must be the same throughout a wire of uniform cross-section and material. And the direction of the electric field at every location must be along the wire because current follows the wire. So we know that it has to be pushing all those charges the same way. So we want to think about exactly what's causing the source of this electric field. And we're going to just drift through this and eliminate a lot of options that you might consider before we get to the actual source. All right, so let me introduce a simple circuit. You've been building these circuits in lab for a while now. Basically, it's a battery connected to a light bulb, and the light bulb acts as a resistor. In fact, this circuit is so simple that my 3-year-old figured out how to build it all by herself with no instructions, and I was very proud of her. All right, so we know that the field is forcing the electrons through this filament, generating friction and therefore heat, which is causing it to glow. And we know that the electric fields are produced by charges, so there must be some excess charge somewhere to produce the field inside a wire. But remember, the wires themselves are not charged, so we're trying to think about where are the charges on the wire? And what distribution of charges could produce the pattern of electric field that's following the wire? So that is the mystery that we're trying to solve. How are we pushing those charges through that wire? So let's go through the different circuit elements. Are the excess charges inside the conductors? I mean, maybe. So we've got 2 conductors. The battery is not one of them. So you've got the bulb filament made of some sort of conducting material, and you've got the wire. And we know that there's no excess charge in the interior of either of the above. Remember, excess charge means charged. They would have an equal number of electrons and positive atomic cores canceling each other out. You can kind of see that here. You've got the electron bopping around all these metal ions. So the excess charge must be elsewhere. What about the battery? So the battery is an active element on the circuit. Maybe it's charged. So maybe the positive and negative ends of the battery are basically inducing a dipole-like field. Well, we can test this really easily. So unfortunately, for those of you who are online, you're going to have to test this next time you're in lab and prove this to yourself. It's very simple, but basically you can take a bulb and move it 10 centimeters away from the battery, and then you can move it so that it's about 1 centimeter away from the battery. So if the dipole was charged, you would expect that that bulb would get much brighter by being closer to that electric field because of that distance dependence. I mean, when you get close, it adds up fast. Did you observe that in lab? And no. So it's a little bit too close for the 1 over r cubed relationship, but you can estimate it that at 1 centimeter distance, it would be about 1,000 times as large as 10 centimeters. And so, and if you bring that light bulb closer, it does not get brighter. So clearly, we're not getting a dipole-like field from the battery. We need another approach. So for this, I'd like to introduce you to a thought model of a mechanical battery. Now, this is not exactly how a battery works, but this is a really good way to conceptualize it that will get you pretty close to understanding the physics behind how a battery works. So remember, thought models are not always accurate, but sometimes they serve very useful purposes in helping you conceptualize. All right, so you can think of a battery. We know we've got a positive plate and a negative plate. You could think of the battery having a little bit of a conveyor belt between the two plates, pulling the electrons off the positive plate, making it more positive, and then depositing them on the negative plate. And then these deposited electrons would then repel and then push the electrons around, replenishing the pulled out electrons from the positive plate. And so basically, as long as there is a motor to maintain the charge separation across the plates, you've got a steady current in your wire, which is not unlike how a chemical battery works. Chemical batteries are the kinds that we've been using in lab. It's not like there's a little conveyor belt, but that kind of process is going on. All right, so we're going to use this thought model of the mechanical battery to then think about the field. All right, we drew something that looks like this. So we've got the electric field going in one direction all the way around, and the current going the opposite. But we have okay. So to reflect, we have yet another incorrect model, bummer, for understanding steady state charge distribution. So charge distribution must be something a little bit different than just the field from the battery. Something is driving these electrons to go around this wire. So let's think a little bit more deeply. So what if there's charge buildup on the surface of the wire? Remember, charge buildup is different than charged. So electrons in the sea don't interact with each other because the repulsion is balanced out by attraction. So something else beyond the sea contributes to the electric field that pushes the electrons through the wire. So let's think a little bit more about our bendy wire where we looked at the field. What would happen if the only charges were on the electric plates? Then the electric current would flow towards the left band from both neighboring sections. So we've got here, you'd have electrons going in both directions, and then your current would stop because you have a section where you've got current flowing in but not going out. But what would happen to this section of the wire? So let's think a little bit more. What will happen if electrons are flowing into a wire from both ends? Well, that's going to become a very negatively charged section of wire. And we know wire is a conductor, so electrons are free to move. So all excess charge is going to move to the surface of a wire. So you've got a buildup of charge there. And so it moves to the surface, just like we talked about in chapter 14. So going on, that excess charge, all right, so we want to keep, so the charges on the bend contribute an electric field to the left at 4, which is opposite to the electric field of the mechanical battery. And so the field is going in the opposite direction, is reduced in its magnitude. And as long as the electric field points right, the opposite direction, excess charges will pile up and the electric field will grow. But then you might be asking, wait, pile-up's a problem. Pile-up stops circuits. Well, let's think about pile-up. How far does this pile-up process go? When does it stop? Well, we have addressed ideas like this before with capacitors. Eventually, the pile-up is so great that the net field will eventually point to the left. And eventually points 3, 4, and 5 will have the same magnitude of charge. And when this happens, now we've got our steady state current, that the electron current is equal to NAV average, which is equal to NAUE. And so the electric current will eventually become the same in and out of the bend. So pile-up stops as soon as it reaches steady state. So remember, in physics, things like to go to steady state or equilibrium. If it can't get to equilibrium, it'll settle for steady state. So the takeaway from all of this and how you can think about your currents when you build them is that this charge buildup is called feedback, and it occurs at wire bends. All right, so moving on to 18.5, we're going to understand these surface charge distributions in more detail. So the amount of charge and sign of charge in the wire is going to vary. It's all about making sure that electric field is uniform. Charge uniformity is not important. It's electric field uniformity. So immediately you would see that it's going to be strongly negative, and it's going to get less and less and less. Sorry, left of capacitors over here, strongly positive, right of capacitors, strongly negative. And in the middle, you've got just a little bit of charge as it flips over. And this is called the gradient of charge. So you can see a cross section or a chunk of it here where you've got it going gradually more and more and more positively charged with this cylinder here. And then you can see it going from very negative to nothing to very positive. So this is what's going on in a circuit. You've got a gradient of charge all around the surface of the wires. All right, so here we've got two equally charged rings on the surface of rings. We know that it would be 0 in the middle, and off axis the field would be small and it doesn't point along the surface of the wire. So even if you have very large charges, you can't make an electric field that will align with the wire. So that's a problem if you want electrons to flow. So if we look at the gradient of this wire from the left ring to the right ring, you can see, looking at charge versus position, the slope is 0, meaning the charge doesn't really change from one ring to the other, and so the gradient of the surface charge is 0. And so we need a different way of distributing charges if we want to get those those electrons to flow. Moving on, if we look at a constant gradient of charge, now if you've got two rings with different amounts of charge, both rings are positive, but one has more charge than the other, meaning the field between them is non-zero. So unlike our previous example, where they had the same charge, there's basically nothing going on between them. So, but if it's slightly different, you can see that the field is now going to point along the wire. And so it's going to start to produce a uniform electric field throughout the wire. So you need that gradient charge density to produce that uniform. So now we can understand circuits in more detail. So you would anticipate the following, that when you have long straight sections far from other elements, they're going to have a nearly constant gradient of surface charge. Surface charge is going to be the biggest where the electric fields are the biggest. So think resistors around the battery, etc. And surface charge is very complex in places like sharp bends. We're sticking with the general idea of how surface charge works. Now, if you wanted to really understand it in detail, you could model the surface charges through a series of little squares. So you would start out with a charge only on the battery, which is typically shown in simulations like this as a capacitor. You would divide your wire into little squares because you want to make your life easier. And then you divide the surface of the wires into tiles. And then you would calculate the electric field for every tile due to all the other charges. And you'd use this field to calculate flow. And then you'd repeat this until the distribution no longer changes. Also, you would use a computer program to do this. And no, I am not going to ask you to do this. But if you wanted to understand this in more detail, you could write a computer program to do this. And that's how people who understand this go after it. So if we look at a single wire circuit, we can make it a little bit more complicated by adding a resistor into it. And so you would see that you're going to have a small gradient of charge. On the negative side, that means it's not changing very much. And then you've got a big electric field around the resistor to really push those electrons through, and so you're going to have a big change of charge right where the resistor is. So you can see what that looks like in terms of the charge distribution and plotted on this plot here. All right, so the gist of 18.5. So the image on the right is the field and drift velocities distribution for the simple circuit on the left. So you can see you've got a bunch of charges drawn around the positive and negative sides of the batteries. They get less and less and less as they go around. And then you can see the implications for field and drift velocity. So I could expect you to draw something like this. Very simple. All right, so we're going to move on to what happens after you connect a circuit. So the initial connection. What's going to happen when dot connects those wires? We're going to think about this in terms of charge flow and electric fields. All right, so right before contact, you've got two wires hooked up to your battery, but they're not connected together. And you would never hook up a battery without a resistor. But for this, we're just going to pretend. So this wire is going to be really negative, and this wire is going to be really positive. And if we look at the gap in between the two, then you can see that you're going to have the electric field pointing towards the negative, and then you're going to have a little electric field from the other side going the other direction and the opposite on the positive side. So these are the fields due to the charges on the face of the gap. And so you can see the charge distribution. You'd have a bunch of positive charges here on the left-hand side of the wire and a bunch of charges on the right-hand side of the wire, looking at that gap. All right, so immediately after making contact, so we're talking like femtoseconds, the cross section near the former gap just after closing. So now you've got those positive charges touching those negative charges. And then you can see that the field is going to start to arrange as you have the dilution of the original surface charges. So now things can move, and you'll still have a zero electric field everywhere on the wire except right at the gap. So you'll have your one non-zero electric field right at the point of contact. By the way, this happens really, really fast. And then after contact, very quickly, you've got a steady state circuit. So now you've got the same field, assuming the wires are made of the same stuff, with the same magnitude everywhere along the wires. So now your electrons are just chugging along. And this answers the question that we posed in 17. The light comes on in the time it takes to make a steady state. It's entirely independent of the drift speed of the electrons. So the speed of light determines the minimum time required for steady state. And if you're curious, light travels 1 foot in 1 nanosecond. So yes, if you're making precision measurements, your wire length is very important. And it takes only a little electron movement to rearrange the charges to bring about that field. It's all about fields. All right, so 18.7, feedback. Which you might be most familiar with in terms of microphone problems. So this is the South Bend band Dr. Doctor performing a show in 2009. My husband is in this picture. Can anybody guess which one he is? All right, so 18.7. Feedback, which is that surface charge on the wire, is required to get the circuit going. Remember, it has to do with distribution of charge, not a charged wire. So there must be some excess charge on the outside of the wire, and it's basically that the charges have automatically arranged themselves to enable current to flow. And feedback will turn conductors into equilibrium outside of the circuit. So feedback in a circuit leads to a surface charge and a steady state current of non-zero. And feedback is also in static electricity leads to equilibrium where E net is equal to 0. So feedback is also related to static electricity. So it's going to try to make something that's charged, it wants to go to equilibrium. That's how you get that spark. And that's all I need to say about feedback. So 18.8, surface charge and resistors. Resistors are, as their name suggests, things that resist current flow. Basically, you can think about it is that it works a little bit harder to get those electrons through. So they're going to limit the flow of electricity through a circuit. And they do really interesting things in circuits, which we're going to learn more about. And that's where understanding resistance, a lot of those classic circuit equations comes from this. And the filaments, as we've talked about before in light bulbs, are resistors. Electrons are working hard to get through there. That's why they're generating all that friction, which is then lighting up the bulb. And by the way, these are some common circuit symbols: wire, switch, light bulb, resistor, battery, which we'll go through in more detail in chapter 19. We can also think of resistors in terms of wires. So if you have a circuit with a section of thin nichrome wire, that's going to act as a resistor. It's harder for electrons to go through nichrome. And what would happen then as we flow current through this? So let's think about that. All right, so if we think about that, let's say the nichrome wire is here, and if it's acting like a resistor, you're going to have that big gradient of charge again. So the number of electrons trying to enter the resistor would be Na thick V, and the resistor is Na thin V, so one would expect electron pileup, and likewise there would be a positive pileup on the other side, making that really big charge gradient. And what would happen exactly when the current would be in a steady state? So then you'd have Na thick, Ue thick is equal to Na thin, Ue thin. By the way, as I've said before, you can understand water flow through similar means. So you would see the electric field would go up in the section of the thin resistor. Also, the electron speed goes up to compensate for it. And that's exactly what you would expect in terms of that charge distribution. You've got to force those electrons through that resistor. And you got to do that by making a really nice big field. And you can still have steady state because it would steady stateify there. All right, so let's look at a couple incorrect pictures. So I want you to take the time and think about why each one of these are incorrect before you go on to the next slide. All right, so here we have no charge gradient, so the electric field would be very small, and you've got a huge charge gradient right here, making a big E, which would mean you wouldn't have a steady state. Here you've got almost no charge gradient, so you can't force those electrons through, so that's wrong. And here you've got a large gradient and too small of a gradient. So that's kind of how to think about surface charges. Moving on to 18.9, thinking about this in terms of energy. So charges are conserved, and this is true in circuits. So there is charge conservation in a circuit. We know that any round trip in an electric field is equal to 0, which leads us to current loop roll, which is basically that delta V1 plus delta V2 plus so on and so forth is equal to 0 along any closed circuit path. And this is really just another expression of the energy principle. So let's start thinking about the potential difference across a battery. First, as we start our battery, we would begin to move electrons, in this case from left to right. The charges would build up on a plate and exert a Coulomb force. The Coulomb force is coming from the charges, and it's going to go in the opposite direction as this little non-Coulomb conveyor belt force that is pushing the electrons along. So as the Coulomb force grows, it will eventually be as big as the non-Coulomb force. And the battery is charged up when the Coulomb force from the electrons on the electric plate is equal to E times E coulomb, which is equal to force non-coulomb, that mechanical little conveyor belt force that is coming from the battery. So the ability of a battery to draw charges is determined by quote unquote motor strength, which is really the chemical reactions. So this is an important concept, and we will revisit this as we continue to think about circuits. So commit this to memory. All right, so let's understand some battery terms and equations. So the electric field, or E underscore C is the electric field between the plates. S is the space between the plates. The force non-coulomb times S over E is called the EMF, which technically stands for electromotor force, but it's a bad name for something that is not actually a force. It's actually energy per unit charge. The reason why it has the name electromotor force is they originally thought it was a force, and then EMF became convention, and now we call it EMF, but we do not, other than in physics 2, where we tell you what it means, we never refer to electromotor force ever again. I know, the field of electricity and magnetism is full of bad conventions. Yeah, I don't know what to tell you on that one. I would not choose that if I ran that field, but I didn't run that field. Actually, there was like no women working in that field. Maybe that's why. So EMF is going to be constant and is independent of the current running through the battery. So the role of a battery in a circuit is to maintain the potential difference across the battery and across the circuit. So this potential difference is numerically equal to the battery's EMF for batteries that supply a small amount of current. We will get into different understandings of batteries next chapter so we can understand them in more details. So there's really nothing special about these types of batteries. So you can make a battery out of a lemon. You need, I think, a zinc, a copper penny, and a zinc-coated screw. It will be a battery. It'll just have really high resistance. And so if you wanted to lower the resistance in a battery, you'd basically need to have a better conductor. And we'll get into the internal resistance of a battery in chapter 19. So, or right here. As well. So the battery maintains the steady state. The larger the current, the more electrons need to be transferred. If there is no internal resistance, which would be an ideal battery, then the Coulomb force would be equal to the charge of the electron times the Coulomb field, which would be equal to the force non-Coulomb. And this would lead to the assumption that the delta V of a battery is equal to EMF, which assumes ideal battery. And for a lot of our equations, we're just going to assume an ideal battery. So all of the delta V calculations you've been doing thus far in your labs have assumed the ideal battery. And I will tell you, our batteries are not ideal. Okay, so going back to field and current in a simple circuit, the electric field inside a mechanical battery will point from the positive end towards the negative end, which is the opposite direction to the electric field in the neighboring wires. So the positive end will have a higher potential than the negative end. So if we start to calculate the round trip, you'd have your delta V from the battery and then the delta V from the wire, and this would equal 0. If we start plugging in equations that we know, so delta V of the battery is EMF plus minus EL, which is delta V of a long wire, which we saw in chapter 16. This would be equal to 0. So E is equal to EMF over L. So here's an example to work on. The EMF in a particular flashlight battery is 1.7 volts. If the battery is 4.5 centimeters long and the radius of the cylindrical battery is 1 centimeter, estimate roughly the amount of charge on the positive end plate of the battery. Is this amount of charge sufficient to repel a positively charged piece of invisible tape? All right, moving on to the loop rule. Now, we've been talking about it. Here are the equations in detail. So you'd have delta V1 plus delta V2 plus delta V3 plus delta V4 is equal to 0. In this case, it would be from A to B, B to C, C to F, F to A. And so this would be a circuit with several devices connected with copper wire. Just a note, so delta V4 is approximately equal to 0. Thick wires have high electron mobility in a large cross section, so you need a really tiny field to drive a current. Technically, there is some resistance there, but very little, so we just treat it like it's perfect. And that's good enough. So here's an example. Suppose that VC minus VF, so we would be going from F to C, is equal to 8 volts, and VD minus VE is equal to 4.5, so here to here. What is the potential difference VC minus VD? So here to here. If the element between C and D is a battery, which end is positive? All right, so 18.10, some applications of the theory. Obviously, this has nothing to do with string theory. I just think this joke is funny. So the applications of what we've been learning so far is something called the current node rule or junction rule. So in the steady state, for the many electrons flowing into and out of a node, you have electric current is In is equal to I out, where I is equal to NAUE. We did see this earlier in the chapter. And conventional current In is equal to I out net, where conventional current I is equal to Q NAUE. This is important. You will see this equation comes up on a lot of standardized exams. In the steady state, for any round trip path, delta V1 plus delta V2 plus however many delta V's there are will always sum to 0. And so we've got one more sort of summative problem to work on. The circuit on the right contains a low resistance mechanical battery that exerts a non-Coulomb force Fnc to move electrons through the battery with negligible resistance. The end plates of the battery are very large compared to the distance 0.1 L between the plates. Two thin nichrome wires of length L and cross-sectional area A connect the battery to a thin nichrome wire of length 0.6 L and cross-sectional area 4A. The electron mobility of nichrome is U, and the N, the mobile electrons per cubic meter, or N is the mobile electrons per cubic meter in nichrome. So part A, show the electric field at the 6 locations marked with an X. Part B, show the approximate distribution of charge on the surface of the nichrome wires. Part C, calculate the number of electrons that leave the battery every second in terms of L, A, N, U, and force non-Coulomb. And now we have everything we need to move on to chapter 19, where we can understand circuit elements.